Okay, then let's start. I'm Philipp Gotze. I'm a PhD student from the Technische Universität Ilmenau under the supervision of Professor Kai-Uwe Sattler. And today I want to present to you our topic, transactional graph processing in persistent memory, which we did together with Muhammad Atair Jibril and Alexander Baumstark, who is currently a student at our university, but will join our group soon. Yeah, and as a short motivation or introduction to the topic, so before we investigated previously PM-based data structures like B+ tree, LSM trees, skipped list, tries, and also analytical data structures, or which are more, were done for analytical queries. And yeah, we also applied these in our topic transactional stream processing, where we use them as persistent states in stream processing. And now we thought, okay, what else can we use PMem for? And we saw that graph databases were more and more in demand mainly because of the data, which is increasingly more interconnected or due to IoT and all this stuff. And then we saw that graph queries often have a random access pattern. So they jump from one node to another over the next relation to another, which can or will utilize a random access pattern. And there we thought that PMem would be a natural fit, specifically because of its low latency compared to, for example, SSDs and so on. And also on the other part, we thought, okay, we maybe need also transactional guarantees in this graph engine, and therefore also PMem would be a natural fit with this direct persistence. And with our previous work and also lessons learned from other universities and so other papers we saw, we wanted to apply the lessons learned from this to this work. Yeah. And so to come to these lessons learned, we looked at the DC-PMem, so the Optane persistent memory properties, and also on our PMem-based data structures, and wanted to see what are specific challenges and characteristics of these devices. And we came up with these kind of obvious that PMem has a higher latency and lower bandwidth than DRAM. Then we have reads and writes on PMem that behave asymmetrically in like 3 flavors. So on the one hand, we have the power consumption, we have cell wearing, and also, of course, what I just mentioned, the higher latency, which is a bit higher for writes, and also the bandwidth. Then the DC-PMMs from Intel internally work with 256 byte blocks. Failure atomicity can only be guaranteed for 8-byte aligned writes, which means that we have to take care with software if we need more than 8 bytes. And then, so these before were like direct properties of these devices. And these next are more like challenges which derive from this. So on the first is this PMem allocations are expensive, what we saw. And in one paper, they experimented on it, and we saw it was like 8 times slower than on DRAM. So quite an impact here. And our 6th point is that dereferencing persistent pointers can prevent optimizations. And this is also what we saw in our experiments. If we don't handle this with care or avoid this a bit, then this can cost us quite a lot. Yeah. So when we see these challenges and characteristics, we can directly or more or less directly derive general design goals. So the first 2 are that we want to algorithmically save writes. So because we have this asymmetry and we have a lower latency, that's why we want to save specific operations on these devices. And on the second part, we want to opt for a DRAM PMem hybrid storage design so that not all is on PMem and we can utilize DRAM to achieve better performance. The third point is directly matched. So we want to optimize for access granularity to 256 bytes. And the fourth, as I already said, if we need more than 8 bytes to write, then we need to apply something like logging or shadowing as it is done in PMDK transactions, or we have to manually set stores and fences so that this always has a consistent state. Yeah. At the fifth point, we want to use group allocations. This is not a new idea, but makes much more sense here. And also, instead of deallocating, we should reuse specific blocks and establish a kind of free space management. The sixth point is then that we want to, of course, avoid dereferencing of persistent pointers and use other techniques, and also avoid pointer chasing, which is related to this. Yeah. So these were the challenges or lessons learned we have for our PMem data structures. As we want to look at transaction processing, we have another lessons learned, and this is that we want to use MVCC in our transactional graph processing system. And we saw in an empirical study from the Andy Pavlo group that the MVTO, so the multi-version timestamp ordering, showed the best performance. That's why we also opted for this approach. And we, on top, did our own measurements with MVCC in our transactional stream processing system we built before in PMem. And there we saw that here, especially MVCC is the most scalable solution. So this is the green line here. We compared it with a strict two-phase logging protocol and a backward-oriented optimistic concurrency control protocol. And as we can see, even if we increase the threads from 4 to 20 to 40, then we could see that still MVCC stays the most scalable solution. And that's why we opted for MVCC and specifically for the MVTO protocol. Yeah. The only questions which are open now are how do we fine-tune it for PMem? So this is not completely defined how this needs to be implemented. And that's why there's a bit of fine-tuning what we could do. And we could also apply it a bit different for graphs. Yeah. So these were our lessons learned. So let's dig into our graph database now. So as a short definition, what graph database we are using or which model, we are focusing on a property graph model, which means we have a graph which consists of nodes n and directed relationships, which combines two nodes to one relation. Yeah. Then each node and also relation has a unique identifier, and also nodes and relations can have a label which can define, dependent on the application, a specific type of this node or this relation, but is user-defined kind of. Yeah. And as we have the property graph model, we of course have properties. These are key value stores, key value pairs that we assign to either relationships or to nodes. And these can be all kind of combinations we want and is not limited to anything. Yeah. So this is our model. Then let's come to our design decisions, because we had before the lessons learned, and now we want to apply this specifically for our storage model. And our first decision was, sorry. Our first decision was to have a linked list of chunks for our nodes and relationships and also properties. And these should be cache line aligned and a multiple of 256 56 bytes. And we established a free space management, what I told you before, that we don't deallocate, but actually reuse or not use blocks anymore. Yeah. Then the second one is that we have cache line sized records. So they are all equal size, and this is necessary to actually address them via the offset. So we don't have to use persistent pointers at this point, but can directly address them via offset. This saves space on the one hand, so we only have to use 8 bytes instead of 16. And also we don't have to dereference persistent pointers. Yeah. On top, we outsource some all the properties, so they are not directly stored in the node and relationship tables, but they are outsourced, which gives us another reduction of writes, and also is necessary to actually get these equally sized records. Then we have also a dictionary. This is also necessary. So we have dictionary encoding and compression, which is also necessary to have actually equally sized records. And due to the compression, we get also a reduced writes and spare or can hide a bit of PMem latency. Yeah, and as our last design decision, we opted for a hybrid storage model, which was a second design goal, which I presented before. And we combined here PMem and DRAM to hide the PMem latency. And specifically, we applied it for our indexes and also in the transaction management, which I will show soon. Yeah. But first, to our main data structures. These are the nodes, relationships, and properties. And you can see the nodes and relationships here on the right. So as I said, these are, or is a list, a linked list of chunks. And in each chunk, we have multiple records of nodes or respectively relationships. And yeah, on top, we have here a sparse index, which makes the entry, if we are searching for a specific chunk, a bit faster. Then on the left side here, we have slots, which shows us or gives us a free space management within the chunks. So indicates which records or record slots are free. And then we have the connection here that all the chunks are connected by persistent pointers. This could also be optimized, maybe that we could use some specific offsets here too, but currently these are persistent pointers. Yeah. Then depending if you have nodes or relationships, we have specific fields. As I said, we always have a label as it is stated here. Then we have from relationship list, a to relationship list, so outgoing and incoming relationships, and then offset to the properties table. Yeah, and all of these fields are always offsets. So if we have, for example, multiple relationships for a node, then it only points to the first relationship, and the relationship itself has then a pointer to the next one. So this is if we have multiple ones. Yeah. Then as a last main structure, the properties. These are also organized as a chunked linked list or a linked list of chunks. And there we store key value pairs in batches so that we also can get a 64-byte record size. Yeah. Yeah, on top, so besides the main data structures, we also have index structures, as I said before. And these are necessary for lookup in or lookup queries on node or relationship properties, but also if we want to have an index on labels, this is also possible. And here we decided, based on our preliminary experiments and also on related work, we decided for the FP tree, or FP tree-like design. It wasn't explicitly or directly as it was proposed, but similar. And the main things are that the inner nodes stay in DRAM and only the leaf nodes are in PMem. And on top, we applied, which is specifically for the Intel Optane devices, we applied 256 bytes or made the nodes multiple of these. And then we have, of course, which was proposed by this group, a 64-byte search header, which contains a bit map to show which records or which key value entries are valid and which not. Then we have a fingerprint array, which makes the lookups faster as we stay in the same cache line before going to the actual keys and values arrays at this point. And then we also have a next leaf and previous leaf connection, which is necessary for balancing and also for scanning, of course. And then the padding so that we achieve the 64-byte alignment. Yeah, which also should be applied to keys and values so that they also start at a new cache line. Yeah. And we decided to use this FP tree design mainly because we wanted to have a faster recovery, because we could also have it as a completely DRAM-based B tree. But this would mean that we have to scan for each index a complete graph, and this can be very expensive. So we thought, okay, let's go for the FP tree, because then we only have to scan their leaf nodes, which are much smaller than our whole graph system, and then the recovery is much faster. Yeah. So these are the data structures. Next, I want to go into more detail about the transaction processing. And as I said before, we opted for a multi-version timestamp ordering protocol. And specifically for our graphs, this means that we have, and for persistent memory, this means we have one current version for each object or record, which is always in persistent memory. So here we have some transactional fields I will explain shortly. And then here comes the actual record, and then it points to a dirty list. And this dirty list is or contains all, as the name suggests, all dirty versions, so which are not committed yet, and also older versions from previous transactions. Yeah, and these are completely in DRAM, and we keep only one version persistent. Yeah, and the fields we see here is the first one is a transaction ID, which is actually a timestamp to realize this timestamp ordering, which indicates if a version is locked by a transaction or if it is free or free to use. Then we have a BTS and ETS to show the validity period for readers. So if it is the correct version, they should access, or if they have to search in the dirty list, if there's another version they should have read or should read. Yeah, and then we have the read timestamp, which gives us or tells us which transaction last read this version. And of course, it always shows only the newest transaction to fulfill this timestamp ordering. Yeah, so these are the data or the fields we have here. Now to the operations, excuse me. Now to the operations. For a write, so a write is only possible if the transaction ID is 0 in the first place. So if it is not locked by another transaction. And then, of course, its ID of this transaction must be greater than the last read timestamp of this object, which just means that the transaction must be newer than the last read transaction. Yeah, and if something not holds here, then we have to abort. Yeah, if this is not the case and we are able to update something or insert, then it depends if we update. Then we create a new version in DRAM, and if we insert, then we directly create it in PMem. And of course, these are locked, so the transaction ID is set when we create this new version and put it in the correct place. Yeah, and later to the commit, then we actually apply this, but first to the read. The read searches for a valid version. It starts in the persistent memory, of course, and then it searches the transaction ID if it is locked or not, and if its own ID is between the begin timestamp and the end timestamp. And if this holds, then it actually updates the RTS, so the read timestamp to its own ID, but only if it is newer. If already another transaction read this, which was newer, then it doesn't change this record entry here. Yeah. And the commit works this way that we look on our write set, and then we update first our own validity, which is the BTS, where we set our own ID, and the ETS, so the end timestamp is infinite or infinity. So this is our current or new current version. And on the second step, we update the previous current version. And there we set the ETS, which was before infinity, to this ID or the ID of this transaction. And then we have a new current version. To actually apply this so that others see this, we insert, or in case of insert, we simply unlock this new entry by resetting this transaction ID to 0. And for an update, this is the most complex one now. We atomically have to copy from our dirty list entry to PMem. And currently this is implemented as PMDK or with PMDK transactions. And it works quite good, but maybe we can also later make this a bit faster by manually placing fences and store instructions. Yeah. So this is a transaction processing. The last part to the graph database concepts is our query processing, but this is not the main focus of this talk. That's why I will quickly go over this here. So we provide a push-based approach for query processing, which gives us a basic set of graph-specific algebra operators. As you can see here, we have a node scan, but there's also a relationship scan. Then we have filter. We can also use joins. When we apply or have scanned nodes, then we can later apply for each relationship of each node. And then we have also project and so on. So a basic set of graphic or graph algebra. And this push-based approach also supports multi-threading, which is initiated by these node scan or relationship scan operators. And the subsequent operators, like here the filter and so on, are then executed in the same thread until a pipeline breaker happens, like here the merge, or for example, it could also be a join, but everything else is executed in the same thread, which makes it much more efficient because if possible or if optimal, then everything happens in the caches, which is specifically good for PMem. It is also good for DRAM, but for PMem, it's much more recognizable. Yeah. Besides the node scan and the relationship scan, we also introduced the index scan. So that's why we need the index I introduced to you before. And this makes lookups a bit faster and can look for specific properties on top and so on. Yeah. So this was it about our concepts. Now we have started some initial experiments, and this is first our setup. So the goal was here to first quantify the PMem overhead compared to DRAM. So we implemented, besides the PMem version, also a complete or pure DRAM solution. And the second goal was to find the impact of the concurrency control protocol, so our MVTO, to get a first impression if it is good or not. Our workload was done on the LDBC social network benchmark at the scale factor 10, and we focused more on the interactive workloads as we are more interested on transactions and not on the analytical part of this benchmark. Here's our environmental setup. I don't go through this. If you can press pause if you want to know more details. But our first experiment was on different hardware, as you can see here. Yeah. So here we compared disk, PMem, and DRAM. And as I said, PMem and DRAM is on our own solution. And for a disk representative, we choose Neo4j as a community edition. It's not directly comparable because they have another processing model, and so it's not completely fair, but we wanted to get an impression, how do we behave? And we used all the scan methods I presented to you. So we have the sequential, the parallel, and the index scan. And on the right, you can see here first the update queries. Because we find kind of interesting to see the difference between hot and cold runs. So cold means we executed a query for the first time, and hot means we executed multiple times, but with different parameters. And there we could saw that especially the PMem and DRAM part in the hot runs are very close to each other. So PMem is still a bit slower, but they get very close. And we were quite surprised it works that good, and also results are correct. We tested this, of course. And we also saw that compared to Neo4j, that this gives quite a performance boost if we do it with PMem and still have transactional guarantees. Yeah. Then for the read part, there we don't have actually transactions, but we still wanted to see how it behaves there. We can see that, that also, let me just take this, for example, that PMem and DRAM are very close to each other. So we have here the sequential comparisons, and here we have the parallel. So they are always quite close to each other, which is a good result as we think. Yeah. So this was on different hardware. Another thing we tested was on concurrency control. And here we compared this MVTO, this two-phase locking protocol, and we also tried a two-version two-phase locking protocol. But for the time being, we only support the index scan on PMem, as this 2PL had still some bugs, which we haven't found in the sequential scan. That's why we focus here on index scan. Yeah, but as we see here, the results are not that much as we expected. So yeah, so MVTO we expected to be much better, but as we can see here, it is slightly better than the other ones in most of the queries. For example, here, here, and here too. But it wasn't like that it is or really outstanding here. But we think the main problem is that the LDBC benchmarks here are only short queries and don't have a big contention. So if we would increase the contention and the complexity of the operations, as we have done it in our previous experiments, what I showed in the beginning with our MVCC comparisons, then we expect MVTO to scale much better. Because here 2PL and the other version of 2PL doesn't show any real conflicts or not much conflicts, and that's why it can keep up with MVTO in this case. But still, we wanted to show some first impressions on our concurrency control here. Okay, so these are were our short experiments. As a short outlook on top, we wanted to add, or we already added, a just-in-time query compilation, but we wanted to investigate this a bit further. And we wanted to use this query compilation, or wanted to use PMem in this part as a materialization point. So where we put already generated code that can be used later on or reused later. And also we implemented an adaptive approach, which can switch between the ahead of time compilation and the JIT compiled code. And we also did some first experiments, and it was pretty good results that we see that especially for PMem, this adaptive approach where we switch between ahead of time and JIT compilation was quite beneficial for PMem. Three other things we want to look at in a later stage of this project is the NUMA-aware partitioning. So currently we just put everything in one pool and then assign the chunks to threads. But we want to make this a bit NUMA-aware in the future. Then, as we have seen this MVCC, we have seen some first results, but we want to elaborate on this a bit further in the future. And also specific underlying data structures like the dictionary, we want to look into more detail if we can get a better performance out of them. Yeah, so then I'm at the end of my talk. Here you can see a short summary what I talked about or what is especially useful for the community. So first we presented general design goals which are not only applicable for graph databases, but also for other data structures like that you want to algorithmically save writes, you want to opt for a hybrid storage design, we want to optimize for access granularity to 256 bytes. Failure atomicity has to be handled with care and should be fine-tuned. Then we have to use group allocations and a free space management instead of allocating when needed. And as a last point, we want to avoid dereferencing of persistent pointers. Yeah, as explicit contribution to our community, we provided the data structures we implement for PMem and the according algorithms in this GitHub link or GitHub repository. And we also provided our graph databases or graph database also on GitHub. But of course, we have to say these are educational prototypes. These are no products. So we are always open to bug reports and other input, but still wanted to share with you what we have found out. And yeah, then I'm at the end of this talk, and I thank you for your attention.